of the composite function. So that's just a rule of thumb that we normally use of the composite function. So let's look at an example here. Ready? So what is the integral of x cosine of, let's say, 3x squared dx? Now, when we do this, what's going to happen here? We need to do a substitution because it's not so clear, because this is cosine, this is x. There is no direct relationship between cosine and x that we can actually use to use any of the properties from before. So what we're going to do, we're going to use a substitution, right? Your substitution, you can make it be anything. It could be any letter you want, but in math, we normally use a substitution like u. So we're going to say, let u be equal to, and remember, we normally substitute for the inside function of the composite function. So the composite function here would be cosine of 3x squared. Now, 3x squared would be the inside function, and cosine would be the outside function. So always substitute more than likely for the inside function of the composite function. So we're going to say that u equals 3x squared, right? Now what you're going to do, you're going to differentiate this. So I differentiate this now, so du over dx is going to give me a 6x. Now what we're going to do, we need to actually change this differential here. We need to transpose this differential for dx. So when I do that now, guys, all I need to do is that du is going to be equal to 6x dx. Now, meds this is pretty neat, and I'm just going to show you one time. Ready? So what I can do now, realize that there's an x here. Let me change the ink color so you guys can pick it up. Realize that there's an x here and there's a dx here, right? You guys seen that same x dx here? Cool, so we can leave it as is. All right. So what's gonna happen now? I'm going to get that du over 6 is just going to be equal to x dx. So using this substitution now, right? This integral that we started with, what we're going to do, we're going to change them out. So it's going to give me the integral of cosine 3x squared. Remember we said u is now 3x squared, so that's just cosine of u, cool? And then x dx is equal to du over 6. This 6 here is a constant, so I can actually move it to the front of the differential, which is 1 over 6, integral rather, over cosine integral u du. Simply all I need to do now is just integrate. So when I integrate this now, I'm going to have 1 over 6, and the integral of cosine u is just going to give me sine u. So the answer here is 1 over 6 sine u plus c. But something you must remember, you did not start with a u. You used the u, the variable u, as a means to an end. So you now have to resubstitute it, right? So the final answer is 1 over 6 sine of 3x squared plus c. And that's how you'd use substitution. So remember the rule of thumb, use the inside function of the composite function. That's what we normally use. If it's not so easy to pick up, then your examiner will normally tell you what substitution to use. All right? Because it's really hard for you to just sit down and look at something and figure out the substitution. So let's look at this one here. I probably won't work it because we're running out of time, but I just want you guys to look at it and tell me if you can pick up what the substitution should be. So remember the rule of thumb is always substitute for the inside function of the composite function. So quick and fast, can anybody tell me what would be the substitution for this question? Anybody? Can anybody tell me the substitution for this one? Yes, Jordan, you're perfectly correct. So remember, look for the composite function, right? A function that looks like it has two different parts. So if you realize in this one here, this is composite. How is it composite? Because you have the x minus 1 part to it, and you also have this, that, everything there being raised to the 5th. So the two functions that you could possibly look at is f of x equal x to the 5th, and g of x equal x minus 1. So this composite function here would be f of g of x, which is x minus 1 all the way to the fifth. So what you do, guys, is always look for a composite function when you're trying to do a substitution, right? So the substitution here, I'm not going to work it because we're running out of time, and I want to show you guys integration by parts. So the substitution here would actually be, so the substitution here would actually be, let u equal x minus 1. All right, so once you do that, then it would basically work out to give you something very, very useful. So let me start off the solution for you. So you differentiate this, du by dx is going to be equal to 1. Then it implies to me that du is equal to dx, right? Now why we do that? Because we're using a substitution, we need to change out the variables from x to u, right? When I do that, what we're going to get is integral of x bracket x minus 1. X minus 1 is now u. So times u to the fifth, and dx here now is equal to du, so I can change that to du. But if you look, we still have an x variable, so we actually need to get rid of that. How can I get rid of this x variable? We're going to use this definition up top. So when I transpose for x here, it tells me that x is equal to u plus 1. So plug this in now, I'm going to get u plus 1 times u to the fifth du. Solving this now, what you'll do, you'll expand it, you get u to the sixth plus u to the fifth du, integrate that, and then substitute at the end of the day. So I just gonna leave some dots here. You can do this. We believe in you. All right. So I don't want to do it because we're running out of time, right? So you can definitely do that one. In any other case, as if you couldn't get it, when you do it, if you're not able to get the substitution right away by looking at it, your examiner will more than likely tell you how to substitute. So nothing to worry about. But the general rule of thumb is that if you can identify a composite function, we normally, not always, but normally substitute for the inside part of that composite function, right? Now, on to one of my favorite parts of differentiation. I'll be completely honest, not differentiation, integration. I'll be completely honest with you. When I first did this in upper six, I was just like, what is life? Because this never made no sense to me. My teacher in upper six wasn't the best, but he was trying. But I got the idea of it, but it wasn't so solidified until I had to teach it again. So integration by parts. All right. So integration by parts is a beautiful part of mathematics. And I love it because you can actually see where this method comes from. So if you remember the product rule from differentiation, right? So the product rule from differentiation says to us that if I wanted to differentiate d by dx of two functions, of two variables u and v, or two expressions u and v, where they're both in terms of x, then we know that it'll be equal to u dv by dx plus b du by dx. This is what the product rule says to us, right? Now, here's the thing. If you realize currently, there is a common factor of dx everywhere. So what we can do is possibly cancel that out in a sense, right? So what we get now is we're going to have duv, in a sense, is equal to u dv plus v du, right? Now, let me drop the d at the back so this makes a little bit more sense to you. Now, what we're going to do, we're going to integrate everything here. So we're going to integrate throughout, right? When I integrate throughout, the integral and the differential over here would cancel each other, so I'd actually get uv, right? Now, I can't integrate u with respect to v because u is a function of x, not a function of v. So that's going to be the same thing there. I can't do this, no, I can't integrate v with respect to u because v is actually a function of x and not a function of u, so we can't simplify that. So this is what we have currently, but how can I actually get integration by parts from this? So what you're going to do, I'm going to transpose to this portion here. So what I'm going to have, I'm going to carry this over here to the next side. So I'm going to get that uv minus the integral of v du is going to be equal to the integral of u dv. And this is exactly how it appears on the exam papers, right? So this is what we call integration by parts. And it comes from the product rule of differentiation. And it's a beautiful method, all right? So let me just rewrite it on our new page. So integration by parts says to us that the integral of u dv is equal to uv minus integral of v du. Now, there is something I want you to pick up here. So you realize that we're going to have two functions. We're going to have u and dv, right? So when we're integrating a product, you realize that we'll have a function u and we'll have a function dv, right? So we have u and we have dv. If you look at the other sides, from it, we're going to need, we already have u, so we're good with that, but we're going to need a v. Only way I can get a v is if I differentiate, if I integrate the dv, so I need to integrate this, right? Now, also, you realize that I'm going to need a du. Only way I can get a du is if I differentiate this. So, the whole essence of integration by parts is that you must be able to identify one part of the product to differentiate and one part of the product to integrate. And I'll be completely honest with you. This is where I basically lost all my brain cells in sixth form because my teacher was not letting us know how to choose them. So there's a selection system, I guess, that we like to call. So there's a selection system for the differentiation. So there's a selection system for which one you differentiate, right? For which to differentiate. So this is how the hierarchy works. So we have what we call ILATE, I-L-A-T-E. So once you can remember ILATE, then you'll know which one to differentiate and which one to integrate. So the first preference that you always take to differentiate is what we call the inverse trig functions. So inverse trig functions. And that would mean something like sine to the minus 1 of x, cosine to the minus 1 of x, stuff like that, right? If not inverse trig functions, then we always go to logarithmic functions. And by logarithmic functions, I mean something like ln x. It's highly unlikely, but it is possible, but highly unlikely that they'll ask you to integrate any other functions, right? Highly unlikely. The next one is what we call algebraic functions. Algebraic functions are basically polynomials. So if you see x squared plus anything with polynomials, right? So x squared, x cubed, anything of that sort, right? Then after that, we'll normally go to trigonometric functions. So trig functions, and you know your trig functions are sine, cosine, tan, and them something there. Cool. And then after that, we'll have what we call exponential functions. And the exponential functions will be something like e to the x and something like 2 to the x, something of the sort. Now, what students mostly say misinterpret about ILATE is that they'll normally mix up algebraic and they'll normally mix up exponential. Algebraic, guys, the power is in the base. So you realize that it's x in the base. For exponential, the base is in the power. Oh, I think I just said foolishness. So let me say that again. For algebraic, the variable, not the power, the variable is in the base. For exponential, the variable is in the power. So what I'd like to demonstrate now is one example of how you do this. So ILATE with one of the past paper questions that I saw on your exam. Ready? So on one of the past paper exams that I looked at while I was preparing for the class, a question asked students to say integrate x squared e to the x dx using integration by parts. Now, I want to make your life as easy as possible because I'd love if you love math as much as I do, right? So what we're going to do, we're going to set up a quick table, and the table basically saves a lot of time. So we're going to set up